In today's lesson, we're going to do line of best fit, and we're going to use Desmos with it. The line of best fit means an approximation of a straight line to represent the trend in the given data. How do we know if the model is the best fit? There's going to be two options we can look at. When we do it on Desmos, we'll look at the r squared and we'll see that that value will be a close decimal number to 1. On paper, the line most closely will pass through the given trend of the plotted points we have.
Steps to use when finding the line of best fit on Desmos are going to be the following. Step number 1 is click the plus icon, then the table option. We'll enter the given data into the table, and then we'll click the icon to the left of the table to show a linear regression. We're going to select the linear regression option in the drop-down menu if the problem states that it's linear regression or a line, or if it's the best fit for the data, which we'll look at later in the course. Then last but not least, we'll use the equation given to answer the questions. If you ever have trouble seeing your data points in line of best fit, hit the little plus zoom fit option, it looks like a magnifying glass, to be able to see your data. In example number 1, we have Bill rode his bike to a store 5 kilometers from his house. The table shows the distance from the store paired with the number of minutes after leaving his house. Write an equation that best represents the situation. Round to 2 decimal places. So we're going to go ahead to Desmos here and type in the table. If you would like to, please pause the video so you can follow along. Once you have the table, we again go ahead and hit the Add Regression button. You'll see the drop-down menu has a bunch of options, but we want to select linear regression. As a reminder too, the plus icon here is how we got that table. Now we go ahead and look at the equation given. The equation's right here, and we're able to actually press this button to copy it down so we have it fully. Rounding to the two decimal places is why I have my answer of y equals negative 0.27x plus 4.86. The negative 0.27 represents the slope, and we want to talk about what that means in the context of the problem. Slope from the equation is negative 0.27. So we always start the context slope statement with the y units. So that's why I said the kilometers from the store, because that's the y values in my table. Then I follow that by decrease if it's a negative slope, whereas if it was a positive value for a slope, we would put increase. By, and then we put the number. Then we always write per as our ratio number. And then we go ahead and write a 1 with the units for our x here. So that will kind of always be our format for context writing slope. What does your y-intercept b mean in this context? And does it make sense? Well, the y-intercept is going to be what's added or subtracted after the x in our linear regression equation, 4.86. So the y-intercept of 4.86 represents the starting distance from Bill's house to the store. That does make sense for the value since the problem included the initial value as 5 kilometers. And our approximation prediction of 4.86 is pretty close to that value. In the next example, we're going to have the value v of a computer between year 0, which will represent as 2000, and year 4, which will represent as year 2004, is given in the table. As a reminder, we go ahead and plop that table in Desmos. We go ahead and then hit the Add Regression little icon. And of course, I want to zoom fit with that little magnifying glass to actually see my data. So that's going to go ahead and be my linear regression. As a reminder, this is my equation here. Y equals negative 78x plus 720.4. Remember, I can click that button to copy it down to be able to use it. Now, I want to talk about what the slope represents in this situation, and that's going to be talking about the negative 78 in front of x. I'm going to teach you a trick of how to represent slope. Slope m is always going to be represented by the y value. So the computer's value is our y value for this problem. Then we go ahead and say increasing or decreasing. It's increasing if it's a positive number, decreasing this time because it's a negative number. And we put the number itself here. And the last formulation of this is we do per, or in this case, every 1x value. So you always use 1, and we'll talk about the x value here. So our statement reads slope m represents the computer's value decreasing by $78 every 1 year. Now we want to find the predicted value of the computer in year 8. Right away, I gotta know that means 2008, but I plug in 8. I just got to figure out, is that my X value or my Y value? And I go to my table. The year is labeled as the X value. So that's going to be plugging 8 in for X in my equation. So going to Desmos, I go ahead and delete out X and replace it with a parentheses 8. And I get my answer. 96.4. That's what I'm going to answer and put units on it. I have to put the units of my Y value, which is going to be the computer's value in money. Now I want to find the approximate year after 2000. The computer would cost $325. So that's going to go ahead and be the information I'm given. I go ahead and highlight that number. The dollars is talking about the Y values for my table. So when I go to the equation, I copy down. This time I replace the Y with 325. And I keep the X. Looking for that on my graph, I can see it's at around year 5 here. We'll estimate it to the whole number years since we're talking about years here. So we'll say 5 years specifically after. If you wanted to actually write the year, that would represent 2005 because that's 5 years after 2000. Example number 3, we have the table below shows the data collected on the number of hours a group of students studied for a test and the score each student earned on the test. So hours spent studying versus the scores on the test. So as a reminder, we go ahead to Desmos here. I'm going to hit plus and then table. Please go ahead and pause the video if you need to type in that table. Once you have the table typed in now, you can unpause and click the Add Regression button to the left of the table. And of course, I like to hit my magnifying zoom fit to look at my data here. The equation they give me, I'm going to copy it down so that way I can use it to answer the following questions. The first question we have is letter A. Based on the line of best fit, which is the closest to the score a student could obtain from studying for 4 hours. Right away, I determine if I'm given the X value or the Y value of my data. Right away, I'm going to go ahead and notice that I was given 4 hours. So that's going to be my X value because hours was the independent X value of my table. So what I'm going to do is I'm going to replace X in my equation with the value they gave me of 4. So right in Desmos here, I'm going to go ahead and delete out that X and put a parentheses 4 instead. As you see, it gives me the value. I'll go ahead and round to 100 here. That's a pretty good score for a test, 100%. How long did a student study if they received a 95 on the test? So right away, I determine that I'm given the score of the test, which is my Y dependent value of my table. So that needs to be replacing my Y in the equation. This time, the answer is not going to come up on the left of Desmos if we take a look. It's going to go ahead and end up being on the graph itself. What I mean by that is, do you see when I typed in the 95 in place of Y, I ended up getting this red line going through my black line of best fit and giving me the following point. I was given the Y value of 95, So I want to answer with the x value as the number of hours. 3.4 will be what we go ahead and write here. And of course, we want to go ahead and label the units so that way we know what the 3.4 means in the context of the problem. When we're going to be talking about the y-intercept in context now, I'm going to be referring to this plus 63.80355. I'm going to state that that y-intercept in the context means at 0 hours of studying, a student's predicted test score would be 63.8%. Does this make sense is the second part of this question. And I'm going to say this. While this value is a value you could receive on the test, 63.8 is a viable score for a test, doing zero or no mathematics work and studying in and out of class would probably not get you a 63.8 passing score on a test. But again, possible in the range, just not likely. Last question is, what investigative questions could be asked to collect further data to predict test scores of these students? When I think about questions, and there are so many answers to this, I'm thinking about what else could predict test scores. So two things I thought of are, can their quiz scores predict the score each student will get on the test? Maybe if they did well on the quiz, they'll do well on the test since there's similar material on it. Another question I have is, can the number of assignments completed on MathSpace predict test scores? Maybe if they completed all their MathSpaces with a pretty good passing grade, they might get a good grade on their test. And maybe if they did no MathSpace, maybe they would get a lower score. Could be interesting to see. So again, you want to think about tasks or collectible data. You can then see if it predicts a test score. Now we're going to look at types of correlations given scatter plot graphs. We go ahead and first have a positive correlation. That's going to be as x values increase, y values increase as well. When we talk about positive, we're going to talk about a positive slope, which is rising from left to right. As you see here, we mentioned that we have a weak positive correlation. And that's because we have points that are pretty far away from the line of best fit. Notice for the next one, it says strong correlation because as you see with the blue line of best fit, the points are very close to, almost all are touching that line of best fit. That's when it's going to be strong here. We go ahead and see that it's negative, strong and negative, because we have a negative slope overall. As we go from left to right, E decreases. That's why our statement is, as x values increase, y values decrease. For the last one, there's going to be no correlation case, and that's going to be when we have no pattern between the independent x values and the dependent y values here. As you can see, in the graph, there is no pattern, no correlation. We're going to look at example number 4. The scatter plot shows the number of bushels filled and the number of apples picked. We want to select the equation for the line of best fit. Right away, I'm going to look at the elements of my equation, and that's going to be what's in front of x. That's my slope here. If I sketched a line of best fit here, I would see that from left to right, it's going to be rising. So that means I have to have a positive slope, which is only selected for B here. So that's going to be our equation of best fit. You can also type both of those in Desmos and look at the visual to see which one matches. About how many apples can be placed in 12 bushels. So right away, I want to see what 12 bushels represents. And that's going to be looking at the label of the y-axis. So right away, I'm looking for when y is 12. Well, when y is 12, I look horizontally across that whole line, and I see the point in my data approximately at the x value of between 200 and 300. We'll say 250 as an about. And of course, we want to label it and answer the question of apples. Use the label of your x-axis to label it here. We're going to now talk about the correlation here. We're going to say that it has a strong correlation because with that blue line I drew, all those points from my scatter plot are basically touching it, which makes it pretty strong. We talked about what slope that blue line has, or the trend in the data. It is trending for a positive slope, so we say positive correlation. Now, think back to what we talked about when we have a positive correlation. This statement, as x values increase, y values increase, will be copied for the problem. In example number 5, we have the graph showing the distance bicyclists have remaining in relation to the amount of time they have been riding. We want to answer the first question. Can you predict the distance at 10 hours? So right away, I have half steps for my time. So that means I'm going up by 0.5 on my x-axis. So that means my graph would extend beyond here. But as you see, if I connected a straight line from that line, I would go ahead and be trending towards negative distance. And because 10 hours would be way out here per se, and that would be talking about a negative distance, I cannot have that as a prediction. So my answer is no, because the predicted distance would be negative and we can never have negative distance. The biggest thing too is think about the problem. You are counting the hours towards your destination. Once you hit your destination, you stop counting the hours. We're going to go ahead and talk about the correlation now. As you see, my red is the line of best fit, and not all the points are touching it, and they're pretty scattered out. So we will call this a weaker correlation. Now, look at the red line of best fit slope. The slope of that line is negative, so that's why it's a negative correlation. And again, let's look back at our last page. Negative correlation has the statement as x values increase, y values decrease. So let's go ahead and highlight that.